Okay, this is the first of several videos I'm planning to do on group theory, alright? And these are mostly lecture videos intended for undergraduate courses around the world, alright? But some of the topics I'm going to cover are probably taught in the graduate level as well. So, before we get started, I'm going to assume some things. I'm going to assume that you're well aware about logic and techniques of proof, and sets, relations, and functions. Alright? And occasionally I'm going to assume that you know some results from number theory as well. Okay? Now, group theory is a part of abstract algebra, so we're going to keep things a little bit more abstract than usual. Okay? And before we start with group theory, we need to be well aware, or we need to be familiar with concept which is known as binary operation. Now, to define a binary, what is a binary operation? Okay, to define a binary operation, we need a non-empty set. All right, we need a non-empty set. Then, what do we mean by a binary operation? Any function, let's call it f, from the Cartesian product s cross s to s is said to be a binary operation. Alright, so binary operation is basically a function. Binary operation. And by definition of a function, it's really obvious that if we have any two x and y belonging to s, which means xy and the ordered pair xy will belong to s cross s, we're going to have f of xy to be in s. So if we take any two elements from the set S, now let's see, we're just specifying that S is a non-empty set. We're not particularizing S in any other way. We're just calling it a non-empty set. And if we have a non-empty set, we can define a function f on a non-empty set. Now this is the domain, and this is the codomain, and we can find the range later on. Alright? Okay. So by definition of a function, if we take anything from s cross s, we're going to get something out of s. Alright? In formal language, what can we say is that if we take an input from s cross s, then we get an output from s. Alright? So this is all about that. Now, rather than using the usual notations of f, g, h, phi, okay, let's not use phi because it might clash with the notation for non-empty sets. So, alright, so instead of using f and all, we're going to use some symbols like the asterisk. I'll be frequently, not occasionally, I'll be frequently calling it star, and the star itself, okay, and something which looks like this, 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 and so on and so forth. Okay, we're going to use, instead of, yep, we can also use plus, we can also use into, or multiplication sign, cross, or whatever you want to call it. the minus sign, the division sign, all kinds of stuff, okay, instead of F. So if we just replace the symbol F with symbol star, then star is a function from S cross S to S, which means for every xy belonging to S, which can equivalently be written as for all xy belonging to S cross S, what are we going to have? We are going to have star of xy, star of xy to be belonging to S. Okay, star of xy to be belonging to S. So, and also, instead of writing star of xy, we often use the notation x star y. So, instead of writing plus xy, we write it as x plus y. Instead of writing star xy, we shall be writing it as something like this, and so on and so forth. Compose xy as x compose y. Now, this is the reason why I'm not using the notation f, because f of xy would look something like xfy, which looks really not so good. Okay, now this is all about binary operations. Binary operation is a function defined on the set S cross S, alright, whose range is a part of S, and we call the binary operation, this binary operation, to be a binary operation on S. Alright, so let's quickly look at some examples. Let us verify that. Let me turn the page of the textbook I'm holding. Okay, do we have it? Yeah, we do have it. Okay, now the set of integers is definitely a non-empty set. Also, one more thing, I'm gonna assume that you know the properties of real numbers and integers, obviously. And what we are given is a binary operation star z cross z to z or z or whatever you want to call it. Okay, defined something like this: x plus y plus 1. Now this is something, okay, this we're going to check that if the star or x star y, we can write it like this: x plus y plus 1, where plus indicates the usual integer addition. Alright, if this is a binary operation or not. Now let's see. X is an integer, y is an integer. Alright, so x plus y is an integer, and since y is also 1 is also an integer, x plus y plus 1 is an integer. We're gonna check the validity of this condition right here. Okay, validity of the condition that this, or equivalently this, we're going to check the validity of this statement to come at a conclusion that star is a binary operation. Alright, so okay, this is a binary operation. Very good. And if we want to take an example, let's see, 1 star 2, then we're going to get x equal to 1, y equal to 2 plus 1, so this is equal to 4. Basically this means if we take 1, 2 as an input, we're going to get 4 as an output. Alright, this is it. Now let's see. Let's consider star to be defined on as something like this, and x star y is defined as x plus y, where plus indicates the usual addition, and s is equal to -1, 0, 1. Now, is this a binary operation? No, this is not a binary operation, because we can take any x, we can take any y. Let's take 1 star 1. Then we're going to get 1 plus 1, which is equal to 2. But does this belong to S? No. So this is not a binary operation. This is not a binary operation. So this is not a function. In short, this cannot be paired with 0, 1, or 2. Oh, sorry, 0, 1, or -1. Alright, since we cannot pair this element in S cross S, it's obvious that this is not a relation. Alright, we're gonna have -1, 0. Okay, just look at this. -1, 0, -1, -1, -1, -1, -1, 1, 0, -1, 0, 0, 0, 1, 1, -1, 1, 0, and 1, 1. Alright, here we have it, S, and here we have S. So this is basically just a relation, 0, 1, and -1. Now if we add the two elements, this gets paired, this does not get paired, this gets 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 paired, but this does not get paired. So if we cannot pair at least one element on the domain with any element in the codomain, we do not have a function. We do not have a function. Alright, we do not have a function. This is what's happening. And since star S cross S to S is not a function, it's not a function, we cannot say, or we should say that this star right here is not a binary operation, because binary operation means a function. Alright, so this is not a binary operation. Similarly, okay, now let's take S to be 1, 2, 4. Alright, 1, 2, 4. And let's define star to be something like this, x star y as x times y, where x and x times y, this indicates the usual multiplication. Now, is this a binary operation? Obviously not, because if it were a binary operation, this condition would have been true for every x and y. So we're going to show that there exists x belonging to S, y belonging to S, such that x star y does not belong to S. This is the defining condition. This is its negation. Alright? Now this is a defining condition as per the definition of the function. Okay? Alright. Now let's show that this does not hold. Let's take x equal to 4. Let's take y equal to 2. Then 4 star 2 means 4 times 2, which is equal to 8, and this does not belong to S. So Is this a binary operation? No, this is not a binary operation. On the other hand, let's see this one. This is quite interesting. Let's take the set of integers. Okay, x star y is defined by x minus y. Now this is a binary operation because if we take any two integers in any two elements from the set of integers, then by the properties of integers we're going to get something like this. Okay, so for all xy belonging to z, we're going to get x minus y belongs to z. So this is a binary operation. Now let's look at something on the set of negative integers. Alright, let's take the set of negative integers. Let's take the set of negative integers and define a relation like this, where x star y is equal to 5a minus 3, 5x minus 3y. 5x minus 3y. Alright? Now, we're going to show that this is not a binary operation. This is not a binary operation. Why? Because if we take x to be -1 and y to be -2, then x star y will give us something like this. This is -5 plus 6, which is equal to 1. Now, does this belong to the set of negative integers? No. So, this is not a binary operation. Alright? Now, with these discussions, I guess it's clear that the concept of a binary operation is clear to you. All right, so let's move on to some other properties of a binary operation. Now, some textbooks would like to define the closure property of the binary operations. And the closure property states that xy belonging to S, x star y belongs to S. This is called, if this property holds for a binary operation, then this is called the closure property. But by definition, if star is a binary operation on S, then the closure property must hold as per the definition of a function. So the closure property, it's actually redundant, and it's not redundant. I don't know the spelling. All right, this property is actually redundant. Okay. All right. There's some other properties that's not redundant and are quite significant. The first one of them is the commutative property. All right. The commutative property. If this equality holds for every xy belonging to S, not for just some or just for one or a couple of values of x or y, for every value of x and y, if we have this relation, then we say that star is commutative. commutative. And similarly, we have another property called the associative property. Associative property. Associative property. If for every x, y, z in S, if we have x star y star z is equal to x star y star z, then we say that under this condition, not for just a couple of values of x, y, and z, but for every possible value, if we have this, okay, we're going to take x, y, and z independently as per the technique, so-called technique of using this quantifier. If this equality holds, then we say that star is an associative binary operation. Now this makes quite a lot of sense. This expression makes quite a lot of sense. But how does this make sense? Let's see. Star is defined for the elements of S cross S. Alright. Now let's see. We're taking X, Y, Z to be in S. Now since this is a binary operation, this is characterized by the closure property. So X, Y belongs to S. Alright. X star Y belongs to S. And Z itself belongs to S. So we can write that X star Y, since this is in S, this is in S, we can say that X star Y comma Z belongs to S cross S. Alright, so this expression is well defined. Similarly, since Y and Z are in S, Y star Z should be in S, X itself is in S. This means X, Y star Z is in S cross S. So the expression X star Y star Z is X star Y star Z is well defined. Alright, okay, these are the three basic properties. There are several other properties as well. Alright, but these are the three main properties. In fact, just two. Closure property, always, if it's a binary operation. Okay, now let's consider this binary operation once again. And let's define it like this. Now let's see if this is commutative. Is this commutative? No, it's not commutative. Let's take something like this. This is something like this, and this is something like this. These two are not equal, so not commutative. Now, are these associative? 2 minus 3 minus 5 equals 2 minus minus 2 equals 4. 2 minus 3 minus 5 equals minus 1 minus 5, which is equal to minus 6. These two are not equal, so this is neither commutative nor associative. Alright, there are binary operations which are associative but which are not commutative. Alright, which are not commutative. We're going to discuss such examples when we actually begin group theory. Alright, now let's take probably the first example we considered, Z cross Z to Z, X star Y equals star XY equals X plus Y plus 1. Okay, Now this is both commutative as well as associative, since now if we take x, y, z in z, let's see, x star y equals x plus y plus 1, y star x equals y plus x plus 1, right? So this means since the addition of integers is commutative, we can write something like this, and we directly get at once something like this. Okay, now x star y star z. X star y means y plus x plus y plus 1 star z. This means x plus y plus z plus 1, sorry, not z. This is x plus y plus z plus 2. And similarly, x star y star z is equal to x star y plus z plus 1, which is equal to x plus, now this appears instead of y, which gives us x plus y plus z plus 2. So this operation, this binary operation, is both commutative and associative. All right, these are just two examples, two simple examples to illustrate those properties. Now, what do we mean by an algebraic structure? What we have discussed so far is that if we are given a non-empty set, then we can define a function s cross s to s, alright, like this. Now is this operation unique? Obviously not. Obviously not, because we have already considered two different operations, y on z plus 1 on z and x minus y on z. Alright, we've already encountered two different binary operations on the same set. So this is not, the binary operation defined on a non-empty set is obviously not unique. Alright, now what do we mean by an algebraic structure? If we have a non-empty set S and star is a binary operation on S, binary operation on S, then S star, then the set S together with the star is set to form an algebraic structure, is set to form an algebraic structure. S together with star, which is written as S star, an ordered pair S star, is set to form an algebraic structure. Alright, set to form an algebraic structure with one binary operation. And what we are going to study is groups. Group is an example. Group, which we are yet to define, is an example of a binary operation, an algebraic structure, algebraic structure with one binary operation. Similarly, if we have a non-empty set S and star 1, star 2, 2 binary operations or binary operations, two different binary operations on S, then S together with star 1 and star 2 is also said to form an algebraic structure with two binary operations. Algebraic structure with two binary operations. Alright, with two binary operations. An example of this would be ring and integral domain, which is a special kind of ring, and obviously ring, integral domain, and a field. Okay, we will be discussing these on a separate series of videos. Alright, but the basic concepts, they're the same. They're gonna make use of group homomorphisms and whatnots, and yeah, so basically a non-empty set together with the required binary operations defined on it will form an algebraic structure. Alright, will form an algebraic structure. Alright, that's all for today, and in the next video we're gonna define what a group is. Alright, okay, thank you very much.